Okay, welcome back to linear algebra in chapter 5, which we're going to start with this lecture. Kind of the fundamental question that we're trying to answer is under what conditions does an operator admit a basis for which the matrix in that basis is diagonal? Diagonal matrices are particularly easy to work with, so it's often nice to have such a basis. So we'll start off with a definition, just kind of giving a name to when that's the case. I'm going to say that an operator T on a finite dimensional vector space, everywhere in this section, I mean that, unless I say otherwise, is called diagonalizable if you can find that basis. If there's an ordered basis for your space, such that the matrix in that basis is a diagonal matrix. I'll remind you what I mean by a diagonal matrix. It means that we could write T in this basis as some matrix that its only non-zero entries are on the diagonal. Those entries on the diagonal might be zero, and they might not be, but if you're off the diagonal, then you are zero. That's what I mean by a diagonal matrix. Okay? So we'll call a matrix diagonalizable. It's the same adjective applied to a different thing if the transformation defined by it in the standard basis is diagonalizable. Okay? So we have diagonalizable operators in matrices, but the word kind of means the same thing. Just an observation before we go on here, if you do take a diagonalizable operator, then if you pick a vector in the basis, the basis that makes it the matrix diagonal, then it must be the case that when you take t of that vector, you get a scalar multiple of it back. That's because when you take that t of that vector and write it as a linear combination of the basis vectors, the only non-zero coefficient is the one that corresponds to v. That's why it's a diagonal matrix. Okay. So some lingo. Keeping that in mind, I'm going to call a non-zero vector. It's very important. I'm going to write it again just to emphasize it. A non-zero vector is called an eigenvector for our operator if you can find some scalar such that that equation holds. T of v is lambda v. And if you have such a vector, if you have an eigenvector, then the scalar is called an eigenvalue for that eigenvector. Okay, so we have eigenvectors and eigenvalues. Eigenvectors are not allowed to be zero. They're non-zero vectors. And every time you find an eigenvector, you found an eigenvalue. It's the lambda for which t of it is that scalar. Cool. Same thing as above. If I'm talking about these things, eigenvectors and eigenvalues for matrices, well, I just mean that for this linear transformation L sub A. Okay, so that's always going to be the case. If I define something for operators, then I mean the same thing for matrices. I just use the operator L sub A. Cool. There's theorem 5.1 in your book. It's just really sort of an unwinding of definitions. We've already proved it. So T is diagonalizable. Remember what that means. It means there's a basis and for which this matrix is diagonal. Well, that would mean that there's a basis of eigenvectors. So this is just definition. There's nothing to prove here. It's a diagonalizable map if and only if there's a basis of eigenvectors, because an eigenvector by definition is something that does this, and that would force that matrix to be diagonal. And moreover, the diagonal entries of your operator in that basis are just the eigenvalues, just like we wrote above. Okay, so just some terminology. Let's look at an example. I claim that this basis, beta, you can look at the vectors. I claim that that's a basis of eigenvectors for this matrix. So remember what that means. It means that they're eigenvectors for the linear operator defined by left multiplication by that matrix. In this case, let's just say these things are real numbers. So it's going to map R2 to R2. It's a 2 by 2 matrix. So I'm just demonstrating the claim down here. Yeah, if I take the matrix A and I multiply it by that first supposed eigenvector, well, you can check the matrix multiplication. I won't slow the video down. I end up getting -2 times the vector that I put in, right? So this thing looks like, if I wanted to kind of annotate it, it looks like A times V is -2V when I'm done. The second one does the same thing. If you take V to be the vector 3, 4, the other element of beta, you end up getting 5 times 3, 4 when the matrix multiplication sorts out. So the eigenvalues here are -2 and 5 for that effect. Well, where did I get that basis beta? I'm going to show you in a little bit here. I'm going to mention this. I kind of hesitated putting it in because this is not a finite dimensional vector space. So warning, but I think it's worth mentioning because you guys are taking some other interesting mathematics courses alongside this, that the exponential function, e to the ax, it's an eigenvector. This thing, f of x equals e to the ax, it's an eigenvector for the differential operator on the space of infinitely differentiable functions. That's what that C infinity is. It's not a finite dimensional vector space. But what do I mean by that? I just mean if you differentiate e to the ax, you get a times e to the ax, right? So your eigenvalue is a. The fact that the exponential function is an eigenvector for the differentiation operator is a super important fact about ordinary differential equations, among other things. So that's why I'm kind of mentioning that here, just sort of giving you a teeny taste of like this linear theory pokes its head into everything. Any place you're thinking about things where sums and scalar multiples are satisfied, all of this linear algebra applies there. It's just we've been kind of sticking to the linear algebra-like examples only, which is sort of my fault, but it's really neat stuff. Okay. So now, after having that little excursion into the calculus, let's state our main problem. Our main problem is somebody hands me an operator or matrix, doesn't matter, either one. How do I find its eigenvectors and its eigenvalues? That's the problem. So we're going to start by kind of picking that apart. So we're going to find eigenvalues first. Turns out to be sort of a nice technique. So some scalar is an eigenvalue for a matrix. Remember, if you gave me an operator, I would just write down its matrix in a basis and work with that. We'll worry about different bases here in a little bit. So we'll start by just saying, suppose you gave me some matrix. Well, lambda is an eigenvalue for that matrix if there's a non-zero vector. Remember, that's important, such that when you left multiply by it, you get lambda times it for some lambda. Should have included that quantifier. So that's for some. No. Sorry, we said lambda is an eigenvalue already. Okay. So what would that mean? Just kind of recapitulating, that would mean I'd have some non-zero vector such that A times lambda times the identity matrix left multiplied by that is 0. Just subtract lambda v from both sides and factor out the v. Remember, if you're wondering why did I put in the identity matrix, well, this thing in the parentheses has to be matrices. I can't just write A minus lambda because lambda is a scalar. But what you'd get if you factored out that v would be the 2 by 2 matrix with lambda on the diagonal. So it's lambda times I2, that should say. I2. No. Sorry, it's late as I'm making this video. I'm not going to start it again. This is IN. It's not a 2 by 2 matrix. Okay. So let me try to concentrate here. So what does that mean? If that matrix underlined in red sends v to 0, well, that means that v is in its null space, so its null space is not the 0 space. Its null space is not the 0 space. And if that's true, that's if and only if that matrix is not invertible, which by our little excursion into chapter 4 is true if and only if its determinant is 0. So those two, the beginning, lambda is an eigenvalue for A, if and only if the determinant of this thing equals 0. Those are the ones I end up wanting because that's an algebraic condition. Okay, so that's supposed to motivate the following definition. Well, sorry, a little excursion, just summarizing it. The red underlined thing summarized, the book calls it theorem 5.2. A scalar is an eigenvalue if and only if the determinant of that matrix is 0. Okay, so that's the summary. Theorem 5.2 is just sort of red lines. The stuff in between was just the way to stitch it all together. So the proof of theorem 5.2 is written above it. Okay, finally, sorry. That motivates this definition. If you give me a matrix, I'm going to call its characteristic polynomial that thing determinant of a minus t times I sub n. T here is the variable, so I'll call it f of t. It's a polynomial. Eigenvalues, by definition, are the zeros of that characteristic polynomial. The values of t that when you plug them in, you make that determinant equal to 0. That's what the theorem 5.2 says. Let's look at an example. Let's take this 2 by 2 matrix, 1, 3, 4, 2. I'd like to find its characteristic polynomial. Maybe it's weird that I'm calling that thing a polynomial. So I'm supposed to take the determinant of a times t minus I2. Well, t minus I2 is a diagonal matrix that just has entries tt on the main diagonal, right? So if I'm going to take a minus that, well, what am I going to get? I'm going to get what you see written after the determinant up there, like 1 minus t. 3 minus 0 is the same. I get 4 minus 0, 2 minus t. So this is just the matrix A minus t times I2 simplified. And then what am I doing? I'm just taking its determinant, product of the diagonal minus product of the off diagonal, 2 by 2 determinant, multiplying it out, and that polynomial happens to factor, lucky me. So I can see it's 2 zeros. Its eigenvalues, we looked at this before. Now I'm kind of showing you where I got those values. If I take this matrix A, which we used in our example above, well, the 2 zeros of its characteristic polynomial are minus 2 and 5. So that's how I got those eigenvalues in that example that we looked at before, just looking what the definitions mean above. So now the question is, well, where did I get the eigenvectors? Okay, well, let's check that out. Oh, sorry, once again, I don't know my own notes. I want to make a comment about what if I'm given an operator. So remember, two matrices are similar. A and B are called similar square matrices if there's an invertible square matrix of the same size such that B is, say, P inverse times A times P. So the punchline here is that similar matrices have the same characteristic polynomial. Similar matrices have the same characteristic polynomial. Why? Well, let's just check the computation out. If we took the characteristic polynomial of B, it's that thing, and then I'm just replacing B with P inverse AP. The identity matrix is certainly P inverse times P, and then I'm factoring a P inverse out on the left and a P on the right. Property of determinants says, well, I get the same thing as just the determinant of A. That's the characteristic polynomial of A minus Tn. I mean, it's the characteristic polynomial of A. Okay, so remember that, so that's this theorem. Similar matrices have the same characteristic polynomial. Well, if you have an operator T, if you write its matrix in two different bases, those matrices are similar. So I'm going to define the characteristic polynomial of T to be the characteristic polynomial of T beta, where beta is any ordered basis. And the theorem that we have written above says that that characteristic polynomial doesn't depend on beta. If you use a different basis than me, we'll have different matrices, but they're similar. So they'll have the same characteristic polynomial. Okay, important fact. And then moreover, I claim that lambda is an eigenvector for the operator T if and only if it's an lambda is an eigenvalue for T if and only if it's an eigenvalue for the matrix. And my beta is on the wrong side of that bracket. Sorry about that. Why is that true? Well, that's just our usual diagram. Remember how this matrix works. You left multiply vectors in the coordinates of beta, but that diagram commutes, so that's just the beta coordinates of TV, but TV is lambda v, and you can pull the lambda out. Okay, so the characteristic polynomial of an operator is the characteristic polynomial of its matrix in any basis that you like. Nice. I'm going to leave this theorem to you. The characteristic polynomial is always degree n, and its first coefficient, the t to the n term, is either 1 or minus 1. And because of that, if it has degree n, it has at most n distinct zeros over the any field, in particular over the real numbers. I'm going to leave that as an exercise to you. We're going to keep going. This video is long, but what I'm going to try to just hammer through, you can stop it and take a break. Okay, so if we just sort of stop and make an observation, if you give me a non-zero vector that's an eigenvector for an operator t, so it's non-zero, there's some scalar lambda such that t of v is lambda times v, well then that v would be an element of the null space of the operator t minus lambda times the identity. So you can think about an eigenvector just being an element of the null space of some other linear operator. That's what theorem 5.4 says, that a non-zero vector is an eigenvector for t with an eigenvalue lambda if and only if it belongs to the null space of the operator t minus lambda times the identity. All right, so this is kind of our primary tool for finding bases of eigenvectors, how to describe spaces of them. Let's look at an example. If we just recycle our matrix A from above, we've already learned that I want to find the eigenvectors for that matrix A. Right, I sort of showed them to you at the beginning of the lecture. This is how I found them. We already looked at the characteristic polynomial and found that its two zeros are minus 2 and 5. So it has those two eigenvalues. So let's just look at them one at a time. If we take, say, the first one to be lambda equals -2, well, then if I look at that operator, a plus, or sorry, a minus lambda I, I'm writing I2 here because I'm talking about matrices. So that's the 2 by 2 identity matrix. You can check the arithmetic that ends up being the matrix 3, 3, 4, 4, which in row reduced echelon form is the matrix 1, 1, 0, 0. Okay, so in that row reduced echelon form, it's easy to see that a column vector x1, x2 would be in its null space if and only if the sum of x1 and x2 was 0. That is, x1 is the opposite of x2. x2 is a free variable. All right, so if I choose x2 to be 1, for example, then I get the vector 1 minus 1, 1, and any scalar multiple of that vector is also in the null space. And because the null space is one-dimensional, that's a basis for it. Okay, so all the eigenvectors of this matrix A that correspond to the eigenvalue lambda equals -2 are scalar multiples of the vector minus 1, 1. The eigenvector that I kind of produced out of thin air at the beginning of this long lecture. If we take the other one, we do the same thing. We look at a minus 5 times I2. Okay, check that that's minus 4, 3, 4, minus 3. That row reduces to the vector, the matrix, 1, -3/4, 0, 0. In row reduced echelon form, it's easy to see that a vector is in the null space. In this case, if and only if x1 minus 3/4 x2 is 0. So that is x1 is 3/4 x2. x2 is a free variable again, so one-dimensional null space. Just to make the fraction go away, I chose x2 to be 4. That equation forces x1 to be 3. So I can take that as my basis vector. Any eigenvector for the eigenvalue lambda is 5 is a scalar multiple of that eigenvector 3, 4. Those two vectors, -1, 1, and 3, 4, they're linearly independent. There's two of them, so they form a basis for R2. So that's a basis of eigenvectors. That matrix A is diagonalizable. How do we diagonalize it? We change basis. If I let Q be the change of basis matrix from this basis beta to the standard basis, sigma 2, we denote it. You just take the basis vectors in beta and make them columns. You guys can check, do the matrix multiplication, that Q inverse times A times Q is a diagonal matrix with the diagonal entries equal to the eigenvalues of that matrix A. That has to be true because Q inverse AQ is the matrix of the linear transformation left multiplication by A in the beta basis, and beta is a basis of eigenvectors. All right, so Q inverse AQ has to send the first eigenvector in beta, -1, 1, to -2 times it. That's why that column is -2, 0. Yeah, and it has to send the second basis vector to 5 times it. That's why the vector, the second column is 0, 0, 5. Nice. So we found a basis of eigenvectors for the linear transformation L sub A. Let's do one more example just to kind of solidify this, and I'm going to kind of kick some of the computations to a machine here. Let's take the following operator on degree 2 or less polynomials. So, oops, sorry about that. T sends a polynomial to it plus x plus 1 times its derivative. And my question is, well, is that diagonalizable? Is there a basis of eigenvectors? Our theory says that we can answer that question by looking at the matrix of T in any basis that we like. So I'm going to take the standard basis for the polynomial space. and just write down the matrix A in that basis. I'll let you check it. I'm not going to slow the video down, but you can check that's the matrix of T in this basis beta. Okay, so let's find the characteristic polynomial of that thing. Characteristic polynomial is the determinant of A minus T times, in this case, the 3x3 identity matrix. Again, I'm going to let you check out the computational details, but you can work out that determinant. It's easy to work out that determinant because this is a triangular matrix. So the determinant is just the product of the main diagonal entries. And we can see that there are 3 distinct eigenvalues for this operator T. They are 1, 2, and 3. All right. So how do we find the corresponding eigenvectors? Well, we have to look at some null spaces. We could do this by hand, but I'm going to show you how to do it with some Mathematica code. Okay, so I'm not going to go slowly here, but you can kind of stop the video and look at this. You have access to Mathematica as an HSU student. You can install it. So to tell Mathematica what a matrix is, it's a list of lists. So lists in Mathematica are denoted with those curly set braces, and I just put the elements of the main list in as the rows. So this is the first row of the matrix A, the second row of the matrix A, the third row of the matrix A. Okay, I can tell it what the characteristic polynomial is. That's what I'm doing on this line. I'm saying f of t. The underscore just lets t remain a variable, and it's the Mathematica command for determinant is capital DET. So I'm writing it's the determinant of the matrix A minus t times the 3x3 identity matrix. Okay, so there's our characteristic polynomial. Mathematica can factor that polynomial for us. Just recapitulating what we did above by hand. Check it out, the characteristic polynomial, just like we wrote above, it's the product of, well, I wrote 1 minus t, I wrote t minus 1, t minus 2, and t minus 3 above. And where does that minus sign come from out front? That minus sign comes from the fact that the product of the 3 negatives is negative. Okay, so there's our characteristic polynomial. Eigenvalues, like we said, are 1, 2, and 3, the zeros for that. So it remains to find bases for these 3 operators, right? The null spaces of them, sorry. Find bases for the null spaces of those 3 operators. Important little detail. We could do that by hand, but let me just kind of illustrate some more Mathematica code here for you. Okay, so I'm just going to do this one eigenvalue at a time. If I take lambda equal to 1, then here, let me just show you what the code I'm doing here. A minus 1 times the 3x3 identity matrix, well, that's the matrix I need to find the null space of. Row reduce is the Mathematica command for putting it in reduced row echelon form, and matrix form displays a matrix the way we look at it on paper. Okay, so that matrix form of the row reduced form of A minus 1 times the 3x3 identity matrix is written right here. And then from that, I can read off that something is in the null space. I'm just denoting it by n here. x1, x2, x3 is in the null space. If and only if, well, this first row would tell me that x2 is 0, x3 is 0. There's no condition on x1 whatsoever. Okay, so I'll take x1 to be my free variable. If I choose it to be 1, the other 2 variables have to be 0. V1 is a basis for the null space of that first eigenspace that I want to find. Okay, doing the same thing down here. Second eigenvalue was 2. Just to walk you through the code, I'm looking at A minus 2 times the identity matrix. So that's where my eigenvalue is going, right there. The rest of it is the same. I row reduce that and put it in display form. So here it is. And from that, I can read that something would be in the null space if and only if x1 minus x2 is 0. From the first row, x3 has to be 0. So that tells me x1 and x2 have to be the same. x3 has to be 0. I can choose x2 to be 1, and that's my basis. Okay. Last part of the computation, third and final eigenvalue, 3. Where does that 3 go in my code? Right there. So I'm taking A minus the 3 times the 3x3 identity matrix, row reducing it and putting it in pretty form. I can see it right there, and I can read off from that x1 minus x3 is 0, x2 minus 2x3 is 0, and x3 is free. Okay, so if I choose x3 to say equal 1, It dictates that x2 is 2 and x1 is 1, so that's a basis. Okay. So I've got a basis. And by the way, we were talking about polynomials. So what am I writing down over here on the right? This coordinate vector in our basis, remember the basis was 1x squared. So that corresponds to the polynomial 1. 1, 1, 0 corresponds to 1 plus x, and 1, 2, 1 corresponds to 1 plus 2x plus x squared. Okay, so those are the polynomials that correspond to these coordinate vectors in our basis. So if I take gamma to be those three eigenvectors, they're linearly independent. That's a basis because the dimension is 3. So this thing is diagonalizable. And the matrix for T in that gamma basis would be the diagonal matrix whose diagonal entries are the 3 distinct eigenvalues. Cool. If we take the coordinates of those vectors and we stack them in columns in a matrix Q, that matrix Q changes basis from gamma to the standard basis beta. All right, so therefore Q inverse times A times Q should be the matrix of T. It should be that diagonal matrix. And you can verify that by hand. I'm going to just show you the Mathematica code. Here I am telling Mathematica what Q is, putting it in as a list of lists. The lists are rows, right? I didn't display it in matrix form, but what I can ask it to do is to compute this product, Q inverse. So the Mathematica command for the inverse of a matrix is just inverse of Q with square brackets around it, like all arguments in Mathematica. Matrix multiplication is with this dot. So that code right there that I'm underlining in blue is how in Mathematica you write Q inverse A times Q. And again, you guys already know what I'm doing with the matrix form command. I'm displaying it, and sure enough, that's our diagonal matrix. All right, I hope you'll start using some Mathematica or whatever software you're familiar with. Octave, I know, was mentioned, MATLAB. There's lots of software out there for manipulating matrices. Okay, thanks for listening.